In August 2029, a spacecraft is going to rendezvous with a dead metallic heart.
Right, the naked core of a failed planet, just just floating out in the cold of deep space.
Yeah, and the only way it's getting there is by threading this absolute gravitational needle at thousands of miles an hour, using Mars as like a cosmic slingshot.
It honestly sounds completely like the plot of a science fiction movie.
Oh, totally.
But it is actual precise orbital mechanics playing out right over our heads. I mean, we're talking about a mission that requires harnessing the momentum of an entire planet just to reach a piece of shrapnel left over from the birth of our solar system.
It's mind-blowing. Welcome to this deep dive, everyone. I'm your host, and if you're joining us, you know we like to get straight to the mechanisms behind the headlines.
And I am thrilled to be here to unpack it with you.
Awesome to have you. So today, our mission is unpacking this really fascinating May 23, 2026 report from Science Daily. It details NASA's Psyche spacecraft.
Yes, the recent Mars flyby.
Right, this breathtaking flyby. And we are going to decode what this intricate piece of orbital choreography tells us about the hidden secrets of our own planet. Because for you listening, this is not just about exploring some random rock. This is literally about looking into a mirror.
Which is, what makes this data so compelling. When you look at the raw information coming back from this May 15 flyby, you aren't just seeing pretty pictures of Martian craters.
Right.
You are looking at the foundational bones of a planet, captured by an instrument that sees the chemical fingerprints of the solar system.
Okay, let's get right into that flyby then. On May 15, the Psyche spacecraft skimmed just 2,864 miles above the Martian surface.
Which is incredibly close in astronomical terms.
Right, just 2,864 miles. And it aimed its instruments at the heavily cratered southern highlands and sent back these stunning, enhanced color images.
Yeah, the data visualization on those is just beautiful.
It really is. The report specifically highlights the Huygens crater, which is this massive double-ring crater, about 290 miles in diameter, sitting near 15 degrees south latitude.
A massive scar on the planet.
Yeah, I mean, think about that scale for a second. 290 miles across. That is like driving across an entire U.S. state.
Oh, easily. Like driving all the way across Pennsylvania.
Exactly, just a single crater. And before we get to the colors and the cameras, I want to talk about that term double ring description. Because we've all seen pictures of the moon.
Sure.
Craters are usually just giant bowls. What kind of astronomical violence causes a crater to have a double ring?
Yeah, so that is a crucial distinction. When you're dealing with a crater 290 miles across, you are not talking about a simple rock hitting dirt and digging a hole.
Yeah.
You are talking about an impact event so energetic that it fundamentally changes the physical properties of the crust. When an impactor of that magnitude strikes a planet, the sheer kinetic energy released causes the solid rock to behave, well, for a brief moment, it behaves like a fluid.
Wait, so the rock literally splashes?
Conceptually, yes, exactly. It's called hydrodynamic flow. The impact excavates the initial massive bowl, right?
Right.
But the underlying rock is compressed so violently that it immediately rebounds.
Like it bounces back.
Yeah. Imagine dropping a pebble into a still pond. You see that central column of water bounce back up.
Oh, right, yeah.
The exact same thing happens with rock. In smaller impacts, that rebound forms a single mountain in the center, a central peak.
Okay, I've seen those in pictures.
Right. But in a colossal impact like Huygens, that central peak gets way too huge to support its own weight, so it collapses back outward, forming a secondary inner ring of mountains inside the main crater rim.
That is staggered to visualize. The solid surface of a planet splashing and then collapsing into concentric mountain ranges.
It's violent geology at its finest.
And the Psyche spacecraft is flying over this at an altitude of 2,864 miles, mapping it at this incredible resolution of about 2,200 feet per pixel.
The level of detail is unprecedented for a flyby like this.
And to do this, the report notes it used a multispectral imager. Now, I think I understand the basic premise. Like, it captures light beyond just the reds, greens, and blues our eyes can see, right?
Right. It looks at multiple bands of the electromagnetic spectrum.
But mechanistically, how does capturing non-visible light actually tell scientists what a rock is made of? I mean, is it essentially like having X-ray vision for geology instead of just snapping a regular smartphone picture? How do you get from invisible light to, hey, that's a pile of basalt?
Well, it really comes down to how photons interact with the chemical bonds inside a mineral.
Okay.
Every material on a planetary surface, whether it's, iron-rich dust, silicate sand, or exposed bedrock, they all have a specific molecular structure.
Right.
When sunlight hits that surface, the energy interacts with those molecules. Some wavelengths of light are absorbed to excite the electrons in the material, while other wavelengths just bounce off and are reflected back into space.
So it's essentially a barcode.
A chemical fingerprint is a great way to think about it.
A fingerprint, okay.
Yeah. For example, a specific type of iron oxide might absorb a very particular wavelength of infrared light. If the multispectral imager on the spacecraft looks at the surface and notices a sharp drop-off in that exact infrared wavelength bouncing back.
Because the iron oxide absorbed it.
Exactly. The scientists know, definitively, that iron oxide is present right there. So the enhanced, vivid colors you see in the released images, those aren't just for show, they're data visualizations.
Got it.
They assign a visible color to those invisible chemical fingerprints so human eyes can read the map.
Which allows them to sort of strip away the noise. Because the report mentions they're using these compositional properties to distinguish between loose sand, windblown dust, and actual bedrock.
And finding bedrock on Mars is like striking gold for a geologist.
Really? Why is that so hard?
Mars is just a dusty place. I mean, global dust storms constantly coat the surface in this fine, homogeneous layer of material, and that obscures the geological history underneath.
It's basically a giant blanket.
Exactly. So by tuning their multispectral imager to peer through the chemical signature of the dust, they can map the actual crust of the planet. They can see the raw, ancient terrain that was forged billions of years ago during the era of those massive double-ring forming impacts we just talked about.
Man, capturing bedrock instead of just dust is amazing.
Okay.
But let's be realistic for a second.
Okay.
NASA didn't send a billion-dollar spacecraft screaming through the solar system just to act as an interplanetary tourist, taking vacation photos of Martian mountains, right?
No, absolutely not.
Because threading a needle 2,864 miles above a planet while traveling at mind-bending speeds, that seems like an unnecessary hazard. If they miscalculated, wouldn't skimming so close just be incredibly risky? Surely there are safer, emptier ways to navigate deep space. Why take that risk?
Well, you're right to point out the risk because the margins for error there are incredibly tight. But the maneuver, what we call a gravity assist, was an absolute mechanical necessity.
Assist.
Yes. The limiting factor in all deep space exploration is propellant. You cannot build a gas station in the void, right?
Right.
Every ounce of fuel the Psyche spacecraft will ever have was loaded onto it before it left Earth. If you try to reach an object in the outer asteroid belt using only your own thrusters, you will either need a rocket so massive it can barely launch, or
Or you'll just run out of fuel long before you arrive.
Exactly.
So they are using Mars to do the heavy lifting here. Now, I've often heard the gravity assist compared to like grabbing a street lamp pole while running to swing yourself around a tight corner faster, or, hitting a boost pad in a video game like Mario Kart.
The Mario Kart boost pad is a fun one.
But the street lamp analogy always felt a bit incomplete to me. Because the street lamp is stationary. I get that it changes your direction, but where does the actual increase in speed come from?
You hit the nail on the head. That is the exact problem with that analogy. The stationary street lamp explains the change in trajectory, but it completely fails to explain the injection of energy. To understand the speed boost, you have to imagine that the street lamp is mounted on the side of a high-speed, moving train.
Okay, a moving train, I'm picturing it.
If you run up behind that train and grab the pole, the momentum of the massive train yanks you forward, right? Accelerating you to its speed.
Yeah.
And when you let go, you are flung forward exponentially faster than you could ever run on your own. In this scenario, Mars is the moving train.
Right, because Mars is orbiting the sun.
Exactly. It is tearing around the sun at roughly 54,000 miles per hour. So as the spacecraft dives into Mars's gravity well, it essentially hooks onto the planet. It steals a tiny fraction of Mars's orbital momentum around the sun and adds it to its own velocity.
Wait. If the spacecraft is stealing momentum from Mars,
Yeah.
does that mean Mars actually slows down?
It does.
Are you serious?
The physics demand an equal exchange. By accelerating the spacecraft, Mars loses a mathematically real, though practically imperceptible, amount of orbital energy.
That is wild.
Yeah, Mars slows down by roughly the width of a hair over millions of years, and in exchange, the Psyche spacecraft gains thousands of miles an hour of free velocity. It is a brilliant, elegant manipulation of celestial mechanics.
And the reason hoarding all that onboard fuel is so critical right now is because of what happens at the end of the line.
Well,
Right?
precisely.
Coasting through the vacuum of space is relatively easy once you have the speed. But the report highlights that when the spacecraft arrives at its target in August 2029, it has to actually enter orbit.
And entering orbit is arguably the most fuel-intensive part of the entire mission.
Because you have to stop.
Right. You are approaching an asteroid at astronomical speeds, and you have to fire your thrusters in the opposite direction to brake. If you don't have enough fuel to shed that velocity, you don't enter orbit.
You just fly right past it.
You just become a very expensive piece of debris flying past your target into the deep dark. So they conserve their fuel by borrowing momentum from Mars, specifically so they have enough braking power to stick the landing, so to speak, in 2029.
That makes total sense. Okay, let's shift our focus to that destination then. We've talked about the mechanics of the journey, the gravity assist, the multispectral imaging of Mars.
Yeah.
But everything the spacecraft is doing is in service of reaching a very specific, bizarre object, the asteroid Psyche.
The namesake of the mission.
Right. Now, out of the millions of space rocks floating in the main asteroid belt between Mars and Jupiter, why design an entire mission around this one?
Because Psyche is not just a rock. The data indicates it is a metal-rich world, and researchers believe it is the exposed, naked core of an ancient planetesimal.
A naked core.
Yes, it represents a fundamental building block of the solar system that we simply cannot access anywhere else.
Okay, I want to break down that term, planetesimal. We're talking about the early days of the solar system here, right? This is
Yeah.
long before the Earth, Mars, or Venus existed as we know them today.
Way before. That early environment was a chaotic disk of gas, dust, and rock spinning around the infant sun. And over millions of years, gravity caused that dust to clump together into larger and larger bodies.
Okay.
These are planetesimals, the seeds of planets. And as these bodies grew, they underwent a crucial process called planetary differentiation.
Differentiation, meaning the materials inside the planetesimal began to separate based on their density.
Precisely. The early solar system was incredibly hot. You had heat from the constant kinetic impacts of things smashing together, and heat from the radioactive decay of elements like aluminum-26.
Sounds intense.
It was. This heat literally melted these early planetesimals from the inside out. They became glowing spheres of magma. And just like oil and water separate in a glass.
The heavy stuff sinks.
Exactly. The heavy elements, specifically iron and nickel, sank through the magma to the very center.
Forming a dense metallic core. You know, I like to picture it like a celestial peach. Yeah, so the heavy metals sink to the center to form the hard pit, right? And the lighter silicate rocks float to the surface to form the fleshy fruit, the mantle, and the crust.
The peach pit analogy is actually a really great way to visualize the structure, because every rocky planet in our solar system, including Earth, has this exact architecture, a metallic pit surrounded by a rocky mantle.
But Earth still has its fruit.
Mm.
We're sitting on the crust right now. If the asteroid Psyche is just the pit, just the metallic core, what happened to the rest of the planet? And actually, push back for a second here. How do scientists even know they are looking at an ancient planetary core and not just a random giant chunk of metal that happened to form out there floating around?
That's a great question. Let's tackle the how we know first, because it ties directly back to how the solar system works. Metals like iron and nickel, they don't just organically clump together in isolation to form a body the size of Massachusetts.
They don't.
No, the physics of the solar nebula dictate that materials were heavily mixed. The only known mechanism in planetary physics to create a concentrated, massive body of pure metal is that process of differentiation we just talked about.
Oh, because it takes gravity to sort them.
Exactly. It requires a massive gravity well to separate the metal from the rock. Therefore, if you see a giant chunk of metal floating in space, the forensic evidence insists it had to have been the center of a much larger body at some point.
Wow. So the very existence of the metal sphere essentially proves the ghost of the planet that used to surround it.
It's the smoking gun. Which brings us to your first question. What happened to the rock? Where did the fruit of the peach go?
Right.
The answer requires us to appreciate just how violent the early solar system was. It was a cosmic shooting gallery. Planetary scientists hypothesized that millions of years ago, the planetesimal that contains Psyche suffered a catastrophic series of hit-and-run collisions.
Hit-and-run collisions.
Yeah.
Meaning it wasn't just a direct head-on collision that obliterated everything.
Right. It wasn't dead center. Imagine another massive body striking it at an oblique angle. The impact wouldn't be quite enough to vaporize the dense iron core, but the sheer shearing force of the collision would violently strip away the lighter rocky mantle.
Just ripping the crust right off.
Exactly. Now imagine that happening 2 or 3 times over a few million years. The outer layers are completely blasted away into dust, leaving only the dense metallic heart behind, slowly cooling and freezing solid in the vacuum of space.
It is genuinely chilling to think about the scale of destruction required to just peel a planet like that.
Yeah.
But this brings us to the ultimate so what for you listening. Why does studying the pulverized remains of a dead planet millions of miles away matter to us sitting here on Earth? I mean, it's a cool story, but what's the relevance?
It matters because we are trapped on the surface of our own world.
What do you mean?
Well, the Earth's core is roughly 1,800 miles beneath our feet. The deepest hole humanity has ever managed to drill, the Kola super deep borehole in Russia, only went down about 7.5 miles.
Oh, wow. So we're not even close.
We are barely scratching the paint on the Earth's crust. The pressures and temperatures deeper down make it physically impossible for us to ever reach our own core. It is permanently hidden from us.
So Psyche is basically a proxy.
It is the ultimate proxy. It offers a profoundly rare opportunity to directly measure, image, and study the exact type of material that sits at the center of our own planet. By analyzing the magnetic fields, the alloys, and the cooling patterns of this exposed asteroid, we can back-calculate the physics of how Earth's core formed.
That makes so much sense.
We study the dead to understand the living. It is our only real way to understand the dynamo that generates Earth's magnetic field, which, by the way, protects our atmosphere and makes life here possible in the first place.
So we're essentially studying the genesis of our own home by examining the remnants of a world that didn't survive the birth of the solar system. That is, let that sink in for a second.
It's profound.
It really is. To summarize the incredible mechanical journey we've traced today, we started 2,864 miles above Mars, watching a multispectral imager decode the chemical fingerprints of the bedrock, revealing the violent hydrodynamic impacts of the past in the Huygens crater. We dissected the elegant orbital physics of a gravity assist, visualizing a spacecraft stealing momentum from a moving planetary train to preserve its vital fuel. And we mapped that trajectory outward, looking ahead to August 2029, when it will fire those thrusters to rendezvous with an exposed, frozen metallic core.
It is a journey from the dusty surface of one world to the frozen, naked heart of a failed one. And, I want to leave you with a final thought to mull over as we wrap up today.
Please do.
We've talked at length about planetary differentiation and those catastrophic hit-and-run collisions. Well, if asteroid Psyche is truly the stripped-down core of a shattered planetesimal, it implies a terrifyingly chaotic history. So when you look up at the night sky tonight, I want you to remember that it isn't just a peaceful, static painting. How many other shattered building blocks of potential Earth-like worlds are silently drifting out there in the dark asteroid belts? How many unwritten histories, how many naked cores and blasted mantles are floating around us, holding the secrets of entire planets that never quite made it?
Wow. That completely reframes your perspective. The solar system isn't just a clockwork machine. It's a graveyard of early planetary experiments, and we are finally flying out there to read the headstones. Thank you so much for joining us for this deep dive. Keep looking up, keep questioning the mechanics of how things work, and keep exploring the universe from wherever you are.